Hello everyone. Today we're going to solve problem 77 in DeepML, which is calculate performance metrics for a classification model. Now, this is also a problem that's very dear to my heart because it's the second one that I made that got accepted into DeepML, and it's the follow-up to my previous question, calculate confusion matrix for a binary classification model. Now, as you can see, this problem in itself has a mouthful as a statement. That's why it was tagged as medium. But if you were able to solve the calculate confusion matrix, or if you want to check out the video that I made so you can get up to speed, I would highly recommend that you do so before you tackle this problem, as a lot of what you have to do stems from that previous problem. So what we have to do here is, given the results of a classification model, which are going to be given into two lists, actual, which is the actual labels for all of the observations that were inputted to the model, and predicted, which is the predicted class labels from the model, we have to compute the confusion matrix, accuracy, F1 score, specificity, and negative predictive value. And the rest of the constraints are something that I'm going to talk about as I make the code. This is just how the input is formatted and how you have to format the output. So for example, here you're getting these lists, and this is what the output should look like. Now, this, as is tradition in this channel, I'm going to tailor this problem towards beginners. And what I mean by that is that the code in itself is somewhat straightforward, as I said, if you did the previous question. But what's valuable about this question is to learn about all of these metrics that I talk about here in case you haven't seen them before. So I'm going to spend some time talking about the intuition of what these metrics mean, when are they useful, and how they could help with your use case. And then I'm going to dive into the code. So without any further ado, let's dive into the intuition. Last time we talked about a confusion matrix. And just as a summary, a confusion matrix is something that you would use when you're trying to understand the performance of a classification model. And what it tells you, it tells you for certain classes how it is that the values were labeled. So when you look at this first element, you're going to figure out, well, out of all of the elements that have a true label of a positive class, that is 1, how many of them were labeled as that positive class? Out of the negatives, how many were labeled as negatives? Out of the positives, how many were labeled as negatives? And vice versa. And the example I gave as a motivation previously was, we have this cat image classification model in which you look at an image of a cat, you look at an image and you have to say whether there's a cat or not. So in this case, for example, when you have an image of a cat, the true label is 1, and what you could have is that, for example, it's predicting that there's no cat there, or maybe it can predict there's a cat. It all depends on how your model is specified. But for the purposes of this question, let us dive into what it is that we have to answer. So a very natural first question, let's say you have computed this confusion matrix, you can now start to answer questions about the performance of your model. So a very natural question would be, what is the accuracy of the model? And what I mean by that is, you would ask the question, well, how many of the classifications that my model did were accurate? That is to say, how many out of the positives, how many out of the positive observations were labeled as such, and the same for the negatives. Now, if you think about it, this question can be answered by looking at this matrix and carefully picking certain elements from within the matrix. Because what it is that we have to figure out is how many elements there are in our model. That is, how many observations did I have? So I want to figure out of all of the observations that I had in my model, how many were properly labeled. So we know from our descriptions of all of these metrics that the true positives plus the true negatives will represent all of the observations in the model that were properly labeled, because it's all of the positives that were labeled as such and all of the negatives that were labeled as such. So that's going to be the numerator of our fraction. And we're going to put it in the denominator as well, because we want to get a proportion out of all of the observations that we have in the model. But as you have observations that were properly labeled, you also have observations that were mislabeled, which would be the sum of the false positives and the false negatives. And so what the accuracy is going to tell you, the answer to this question is, well, out of all of the observations, how many were properly labeled? And this is how you would represent it using the true positives, true negatives, and all of the other metrics that you compute for your confusion matrix. So using the elements from the confusion matrix, we can start to answer questions about a model. We are able to answer what is the accuracy of our model. Now, that is a fantastic metric as a starting point, but it can have certain problems. So let's say, for example, our database consists solely of cat pictures, right? Let's say, for the sake of argument, we have 1,000,000 pictures in our dataset. All but one of them are cat pictures. Then there's only one picture, which is a picture of a guy. If you compute the accuracy for a model that no matter what image you give it, it's going to say that it's a cat picture, then the accuracy of that model is going to be something like 99.99 and a lot of nines percent. You get the idea. So if you were to look at this number, you would think, wow, my model is fantastic. It predicts so well. It works fantastically well. When in reality, yes, the number sounds pretty good, but there's a problem with the number. And it is that your model is not doing anything. It's just predicting the majority class all the time. And so you can get a very high accuracy in these kind of situations where there's an embellished sample. And although you have a model that in strict rigor doesn't do anything, you can still get a very high performance out of it. So this idea makes us think that maybe there's more that we can ask to the performance of our model in order to figure out whether we have a good model or not. So now that we talked about the accuracy of the sample as a whole, a very natural question would be focusing on a class, how many within that class, inside of the class, were accurately labeled? So inside class, accurate labels. So for example, let's say we're looking at the positive class. We want to figure out of the elements that were labeled as positive in our model, how many of them were actually a positive example, that is, that the true label was positive. So we can again represent that by looking at the elements in our confusion matrix. So what we're looking for is out of the elements that were true and were labeled as true, how many of those represent all of the elements that were labeled as true by our model, which is looking here at the first column of our matrix, how many of these elements are represented by the true positives. So in this case, it would be true positives over true positives plus false positives. And why are we including this? It's similar to what we did in the accuracy case. We're dividing by the correct labels and the ones that were mislabeled. In this case, the false positives represent elements that have a negative true label, but were labeled as positive by our model. So that's why they're also considering this. So when you're working with this metric in the positive class, you have what's known as precision, right? And that's a very fancy name. And you're going to figure it out. You're going to hear about it all the time because it's one of the most widely used performance metrics. And so this can help with alleviating the case that we were talking about before, which is you have a very imbalanced sample. How many of those labels that you have were actually part of that class? Now we have an analog metric for the negative class. As you can imagine, it's going to be computed by true negative over true negatives plus false negatives. And this one is called the negative predictive value. And this one you may not find as easily in the wild. Again, because it's kind of the same as the precision just for the other label. And so if you're interested in one of the classes, you would most likely refer to it as the positive class. But in any case, it's important to know that this one exists, and that's why I included it into this question. Now, we just saw that the precision can help us answer how many elements that were labeled as positive are actually positive. But there's another question that we can ask, which is, out of all of the positive elements, that is inside the positive class, how many were correctly labeled? Correct labels. So this is going to give us another piece of information because it can help us to look at the type of mistakes that you have within one of the classes. And so let's think about it for the positive class. So what we're asking is how many of those elements that were labeled as positive were actually positive. So again, those who were labeled as positive and are actually positive are our two positives. We're going to divide that by our two positives again, because we want to get the full picture of all of the elements that were actually positive. And instead of dividing by false positives as we did before, we're going to divide by false negatives. Why? Because false negatives are elements that in reality are positive, but that our model referred to as negative. And so this is going to tell us, out of all of the positive elements that we have, how many of them were actually labeled as positive. And this metric is called recall. And again, this is a very important metric that's going to show up all of the time. And as we saw with the precision, this one also has an analog for the negative labels, which is going to be how many of the elements labeled as negative were actually negative. And it's going to be kind of the inverse of this one. Not the actual mathematical inverse, but it's kind of analogous. And so this one is going to be called as specificity. Should be an F, specificity. Now this one, again, is not as popular as recall, but it's important to know, and it's very similar. It conveys kind of the same idea. So armed with this knowledge, we can have an idea of what performance metrics we have and how it is that they give us information about our model. Now we're going to see one that's going to answer perhaps one of the most important questions. Now, one of the interesting things about classification models in general is that unless you're overfitting, it's pretty much impossible that you have a model that's going to always label the positives as positives and the negatives as negatives. There always seems to be kind of a trade-off, which is going to be if you focus on reducing the false positives, you may increase your false negatives and vice versa. It seems kind of inevitable, and there's a lot of videos that go deep into this topic, so I'm just going to give you this idea and motivate you to go and look at other resources to dig deeper into this, because it opens up a huge rabbit hole. But the gist of it, or what you need to know for this problem, is that it may be a reality that if you decrease one of them, you may increase the other. And so if you're only focusing on, let's say, the precision, then you're going to focus mostly on the false positives. Whereas if you focus mostly on the recall, then you're only going to be focusing on the false negatives. So it would be very nice if we had a metric that could account for both the false positives and false positives and the false negatives. So if we had something that could look at both of them at the same time, then that would be amazing. That would be fantastic. And lucky for us, there's something that's called the F1 score. And this one is great for making sure that you have a somewhat balanced model. The definition by using the elements from the confusion matrix is kind of a mouthful. So most people just write it like this. It's going to be twice the precision times the recall divided by the precision plus the recall. This is what it's known as an harmonic mean. And it kind of follows the same idea, right, as the other expressions. You have a fraction, and in the numerator, you have what it is that you're labeling, and down you have something that represents how many were properly labeled, how many were improperly labeled. It's just a more complex mathematical expression, but if you were able to calculate all of the previous elements before, you'll be able to get the precision and the recall. So we talked about all of these metrics. As you can see, all of them are just based on the confusion matrix. That's why it's so important to do the problem of the confusion matrix. And when we're solving this problem, we're going to compute the confusion matrix first. But once you have that, you just put all of the elements into the expressions and you're able to solve the problem. So without any further ado, let's dive into the code. Okay, so the first thing we're going to do is we're going to start working with the generate the confusion matrix and then start putting all of these elements in the formulas that we just talked about. So I'm going to take advantage that here we're given this nicely formatted return statement with the names of the variables that we have, because we have to round them up to 3 decimals. So I'm just going to name all the variables this way. Now, let's start by generating the confusion matrix. Now, if you look at the input, the way it's formatted, it's somewhat different from the way it was formatted in the previous question. In the previous question, we had a list of lists where every list inside of the big list had 2 elements. Here we just have 2 lists by themselves. And so we can't generate the confusion matrix in the exact same way as before. But we can circumvent that by doing the following. So I'm going to generate a list here. And what it's going to do, it's going to zip the actual labels, that is the true labels, and the predictive labels. Now, in case you forgot, when you do a zip, let's say, for example, you're zipping these 2 lists, something like this, and you call zip, what you're going to get out of it is going to be something that's going to take the elements in order. It's not entirely a list. If you try to work with it in Python or you try to print it, you'll see that it's an iterator object. But this is kind of what's happening underneath the scene. That's the scene. So what you're going to get is you're going to get something like this. You're going to have the first element from the first list joined with the first element from the second list. And the same thing happens in order for all of the elements that we're looking at here. Right? So you're going to get something like this. And if you look at that, this is the format that we had in the previous question. And this is the format we feel comfortable with in generating the confusion matrix by using the counter. So we're going to do our first step to format the data. Then, as before, we're going to call a counter. What this counter is going to do is it's going to count how many times each instance of these small lists is going to show up in the data. And so in order to call this thing, we're going to call counter tuple for pair in data. That is for all of the pairs that we have here in the data. We're going to first transform them into a tuple, and we're going to count how many times they show up. And I talked a little bit about this in the previous video, but if you're wondering why it is that I convert them to a tuple, in Python, counter is a dictionary, and you can't have lists as keys of a dictionary. You can only have tuples. And there's a whole reason why that happens. I'm not going to dive into that in the video, but that's the main idea. Okay, now, because we want to generate our confusion matrix, what we have to do is we have to get the true positive, false negatives, yada, yada, yada. And the way we're going to get that is we're going to interact with the counts dictionary, with the counts counter. So we're going to call counts 1, 1, which is elements that have a true label of 1 that were labeled as 1. For the false negatives is elements that have a true label of 1 and were labeled as 0. And similarly, vice versa for the false positives, and true negatives are elements that are negatives are we labeled as negative. And now we're going to compute all of our metrics. And I'm going to try to be very careful to follow the convention of the same name as in the return statement, so I don't have to do a mouthful out of that. Okay, so first we need to create the confusion matrix. And as before, this is going to be a list of lists, and all of the elements are formatted in this way. Fantastic. Okay, for the metrics, the accuracy, as we talked before, is the elements that are properly labeled divided by the elements that were properly labeled and the elements that were mislabeled. Now, the precision is looking deep into the positive class, how many of the elements that were labeled as positives were actually positives. And so we also have this specificity, which is the analog for the negative class. Fantastic. Now, we also have the recall, very famous one, which is for the out of all of the elements that are truly positive, how many of them were labeled as positive, and similarly, we have the, oh my God, I mixed them up. No, I didn't. Excuse me. Okay, so you have the negative predictive value, which is going to be true negatives over the true negatives plus the false negatives. Okay, so these are all of the elements that we care about. Oh, okay. I just figured out. I thought that there was something weird here. My apologies. So the specificity is the analog to the recall, which is the elements that were labeled that are truly negatives. How many of them were actually labeled as negatives? Apologies for this confusion. And let me put all of this in the same place. This is what happens when you make a question that's so long, you have so many stuff to do. And the final one that we have to compute is the F1 score. Remember, this is the harmonic mean of the precision and recall. And because we have the precision and the recall, we simply call on them and we don't have to do any nasty algebra to get them. And so we have all of the elements here in the return statement, and we're going to submit the code, and it's going to pass all of the test cases here. So as you can see, this question in itself is not hard, but it's very conceptual, and that's why I made it up. I made it so somebody who's a beginner would get exposure to these types of metrics, also to the ones that are not commonly known, such as specificity and the negative predictive value, and they had a chance to make them from scratch. Now, when you're working with real data, and you're trying to do something related to classifications here, this is the format the data will most likely come in. You're going to have one list for the actual labels, one list for the predictive, or a column if you're using a data frame. And so you would like to combine them and work with them to get all of these metrics. Now, in reality, in production, it's more likely than not, you're going to be using a framework or an API that's going to reduce all of this work into simple one lines of code, but it's interesting to understand where it comes from, and now you can code it out from scratch. So that's it. That was the problem. I hope you guys learned something from this and enjoyed it, and I hope to see you in the next video.